Hey guys, welcome back. This will be our 9.1 intro. This section is going to be a little bit tougher. This is something that we haven't actually, it's something we have gone over. This directly ties back to all of our power rules section. So when we went over exponents, remember we had a whole section of simplifying exponents and what all the rules were. So remember that seemed tough in the beginning, but we really got into it, and then people just picked up the rules because it's just time on task. And it's one of those things. This isn't going to be one of those aha things where you figure something out. This is just there is a rule. This is what you have to do in this certain circumstance. So that's really how we're going to approach this. That being said, we're just going to jump into it right now. When you look at your notes, which I'll show you right now, when you look at your notes, so you've got your vocab up here. I really suggest you look into all that. I'm going to go through them real quick, but there you'll tell there's an exploration part on the bottom. You should do that on your own. I'm not going to spend time going through that right now because I just want to keep this a little bit more to the point. But you should be able to do the exploration. And remember, the exploration shows up on your big ideas, so you can go through it right through with them. So just trying to go real quick through the definitions here. Counterexample, all that means is that is the example that disproves your theory. So if I said there are no blue markers, that would be a fact. There's a blue marker. It's a counterexample. That proves that I was wrong. It's all a counterexample is. Radical expression. A radical expression is just any mathematical written out statement without an equal sign, but it does contain a root sign. So remember, it could have square roots, cube roots, anything. Just like there's higher powers, there's higher roots. So it cannot have an equal sign, though, if it's going to be an expression. So that would be like the square root of 24. That is a radical expression. Or I could say the fifth root of 24. That would be a radical expression. Now, simplest forms of a radical expression. I'm actually going to go to the book for that right now and look on theirs because they give you they just line it out, what is really important. So when you have a radical and simplest form, these are the three things that must happen. And radicand, radicand is just the thing that's being reduced. So no radicands can have the perfect nth powers as a factor other than 1. So what that means is, and we're going to get more into this, the radicand is the number under the radical sign. So I'm going to go back to our camera. The 24 would be considered the radicand, okay? And as we get into this more, this all makes sense, so I'm not going to dwell on that too much right now. No radicands contain fractions, so you got to be able to break them apart. No radicals appear in the denominator of a fraction. And that's not going to be on your homework right now. I was debating on whether or not to give that. I may give that out as a bonus section. I might do that this week. I might do that next week. Maybe just I'll do a quick YouTube video of how to get that done. And then I'll give you guys a chance for some bonus points on that. But now let's get into our core concepts, okay? So these are our rules, and you're going to see these when you go through the exploration. Like I said, I'm not going through the explorations. When you look at your notes, you have them right here in front of you, but I'm going to use the book right now. So let me get rid of that. When you have a radical of any two things being multiplied or any two factors, you can separate it, okay? And all that means is, if I have the root of 4 times 7, I can make that the root of 4 times the root of 7. That's all it means. Even if that was a third root, the third root of 4 times the third root of 7. Okay? One thing to really remember, when you have variables, they're automatically being multiplied. So if I have like the fifth root, sorry, that's fluctuating for you. If I have the fifth root of 7x squared, a to the third, b to the fourth, that can all be broken up into the fifth root of 7 times the fifth root of x squared times the fifth root of a cubed times the fifth root of b to the fourth. Okay? It's just a rule. It is just a rule. Things that are multiplied under the radical sign can be separated and given their own radical sign. It's not the best way to say it, but if you want, it's like distribution. And it actually matches up with our rules before. So some of you guys, I'm just going to do this real quick just to show some of you guys. Let's say I had the third root of 4x squared. Some of you guys might remember this could have been rewritten as 4x squared to the power over root. This whole thing is to the first power, 1/3. And then you could go through and do like the distribution of a power to a power. That's why this rule works. If you don't want to know the why, just know the what. The what is everything under the radical can receive the radical individually. Okay? That's what it means. So if I have something broken apart, again, let's say I have 28x squared and I'm taking the square root. Remember, if I don't write anything here, it's understood there's an invisible 2 there. Okay? So you get the square root of 28 times the square root of x squared. Okay? So now let's keep going. So that's really our first one. And then that's going to take you to our first example. Okay? So I'm going to go through the examples on here, and I'll probably go through. Let me see how many monitoring progress we have, because I just don't remember off the top of my head. I'll go through. I think I messed up my pages. Or it's a bunch of, oh, nope, it's just a bunch of minor progress. So let's just go through and then we'll do them all together, okay? So this is where it gets a little bit more difficult, and pretty much I'm just going to explain how to do this. So using the product property of square roots. What you're searching for is, oh, I apologize. I think I hit the go through on this. So now we're really just jumping into how to simplify. When we want to do this, we want to pull out perfect square roots. So you need to remember your list of perfect squares. I'll write them out real quick for you, and then you should have a list. I added a list of perfect cubes onto your homepage, but you should know your perfect squares. Excuse me, you should know your perfect cubes very soon. So really, you just need to know 1 through 12. Okay. So hopefully we all know 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, 6 squared is 36, 7 squared is 49, 8 squared is 64, 9 squared is 81, 10 squared is 100, 11 squared is 121, 12 squared is 144. So if you need to see that, let me see if I can get this to fit on the screen. You could, I don't know if I can get them all in there. You shouldn't need 1, so hopefully you don't need 2 either. Hopefully you can see all those. I don't know. This is hard to get everything in on. So you could write, I would write out my own list, because you're going to need to be able to use these as factors. Okay. So let me really go back and look at the first problem and explain how we're going to do this. So we're going to find out the simplified version of 108. Please do not put the decimal. We don't want decimals. We want simplified. If you simply put in the decimal, you will get it wrong. Okay. So what I'm going to do is I'm going to simplify the root of 108. Now this is going to take a little bit of work, but what you want to do is you want to list out the roots of 108, the factors of 108, but you're looking for perfect squares. So what you might want to do is just look off of your perfect squares list to see which one of those actually go into 108. Okay. Now it's already up on your screen, but if you didn't have that, what you would do is you just go through your perfect squares list. Okay. So 108 divided by, and we want the greatest perfect square. Okay. Not the smallest. We want the greatest perfect square. You can kind of think of, we are expanding the greatest common factor. Okay. So the greatest perfect square. So we go through, 1 obviously is a factor. 4 is a factor of 108. 4 would work. 4 would work, but it would leave us with something else. So 4 works. 4 is a factor of 108. But let's see if we can find a bigger one. 9. 9 would be a factor of 108. But let's see if we can find a bigger one. 16. 16 is not a factor of 108, I don't believe. 25, not a factor of 108. 36 is. 49 is not. 64 is not. 81 is not. And the rest of those will not work. So when we look at this, we're looking for the greatest factor that is a perfect square. This matches up with a lot of our old concepts. So now I can write this as the square root of 36 times 3. Okay? And I'm going to now use my new rule to break this apart. This becomes the square root of 36 times the square root of 3. Okay? Well, 36 is a perfect square. The square root of 36 is 6. So now I can write this as 6 times the square root of 3. And that is considered simplified. So don't let this be too difficult for you. I know that's easy for me to say, but don't try to understand everything that's happening here. Try to understand what our end goal is and just how to do it. This is just a step-by-step process. You look at the original number. You look for any factors in your perfect square, because this is a square root. If it's cube, you look under cube roots. But you look for any perfect square that is a factor of that number, and you're looking for the biggest perfect square. Take that and then the other factor. So 108 divided by 36 is 3. So the factors, I can rewrite 108 as 36 times 3. Now I break that apart. Now that it's broken apart, the square root of 36 is 6. What I'm trying to do is pull out as many perfect squares, many perfect square roots from this number as I can. That's what is considered simplified. If it can be pulled out as a perfect square root, it gets pulled out. Okay? Now, I'm going to go through some more after this section, but this section is starting to run long, so I'm going to cut this and then get back into it through the rest of the examples, okay?